Hello everyone, we are Group 18 and today our group consisting of Beth, Bhavna, Victor, and I will be presenting our design review. To start off with the problem, rotator cuff tears occur when the rotator cuff tendons are torn and is no longer fully encapsulate the head of the humerus. Since rotator cuff allows for stability of shoulder joint and rotation of one's arms, patients often experience acute pain during day-to-day activities. This injury is often caused by injuries such as falling on an outstretched arm or degeneration due to friction with bone spurs, poor blood supply, or repetitive stress.
It may take several months for them to recover, so rehabilitation exercises are crucial for patients after their surgery. Our goal is to develop a device that can remotely monitor improvements in patients recovering from a rotator cuff injury. So having now understood the basis of this injury, the initial step towards creating the device in question is to develop the appropriate criteria and constraints. So in this next slide, we've outlined the criteria and constraints. A couple of the main ones are, of course, that it needs to monitor shoulder recovery as well as provide accurate data. And another big thing is we wanted it to be wearable. And our main constraint was using the sensor and microcontroller in our 3PO4 kit and keeping the total cost under $200. So moving on to the design process, we've identified issues and also criteria for the solution. So now this is the process of how we actually landed on our final design. Basically, after we brought our initial sketches together, we evaluated and compared them against design considerations that we had previously outlined, one being not contributing any additional pain to the user, as well as measuring motion in all planes and being put on independently. And so after evaluating the sketches under those design considerations, we combined them to create one preliminary design and then gained feedback from mentors and the teaching team in order for us to make improvements and ultimately land on our final design. So the majority of our individual designs centered around cuffs and sleeves, with one outlier kind of being an exercise band that monitored stress and tension. And so using ideas from each of these proposals, we moved forward to create one cohesive initial prototype design. So we initially suggested an arm cuff that rests above the elbow that would monitor ranges of motion in the shoulder, including abduction, adduction, flexion, and extension. And the initial prototype basically just consisted of one sensor, one microcontroller, and one coin vibrating motor. So the aim would be to store the highest ranges of motion and provide a display of these values at the end of each session to give the user and the clinician an opportunity to analyze improvements over time. And then the device would also be used to notify the user of compensatory movements with the use of a coin vibrating motor. So then we presented this to our experts and we gained feedback. And so we came to the understanding that assessing compensatory movements would be much easier to attain with the use of a second sensor on the shoulder. So we were informed that we should consider which muscle or muscle group is being targeted in our search for compensatory movements. And so we could use this sensor on the shoulder to detect muscle unspecific movement and then classify elevations of the shoulder beyond a specific range as a compensatory movement. And so this allowable range of error would differ based on the therapeutic exercise being performed. In addition to the sensor, we were also made aware of sizing constraints. Initially, we thought a one-size-fits-all approach would be best. However, given everyone's different kind of arrangement and measurements, the sensors wouldn't sit in the same spot for everyone. So we decided to incorporate an adjustable feature in the sleeve so the user can easily put on the device with one hand before strapping in, and the device can be tightened and adjusted to ensure the sensors are on the correct area of the arm or shoulder for all measurements of everyone.
So with the design feedback in mind, along with the initial criteria for the solution, we present to you our final device, which is the Smart Sleeve. It contains two BNO055 sensors, one on top of the shoulder and one on the lateral side of the arm, just above the elbow. The device is in the form of a sleeve to be worn around the shoulder and arm, all held in place by a strap that wraps around the torso. And this idea allows the user to put on the device with their opposite arm, considering the compromised range of motion in the affected arm. The sleeve is fabricated as an elastic compression sleeve, retaining non-restrictive and lightweight characteristics to allow the user to complete exercises without extra energy consumption due to weight. And each component will be attached to the brace in order to provide an all-inclusive device. So embedded into the sleeve are four key components. There's a BNO BNO055 sensor on the shoulder that monitors changes in scapular elevation and classifies compensatory movements. There's a BNO055 sensor on the elbow to measure the range of motion of the arm relative to the shoulder, considering adduction, abduction, flexion, and extension. There's a battery-powered ESP32 microcontroller, which is connected to both sensors, and a coin vibrating motor, which will then create distinct tactile sensations to notify the user of either compensatory motion or record high ranges of motion. So we can now go over how our design will address the problem. So the smart sleeve is distributed to patients by healthcare professionals, including physiotherapists, to be used during shoulder rehabilitation. The device monitors improvements in patient recovery by remembering and storing the patient's best or highest values in each plane during each session. At the end of the rehabilitation process, these scores can be analyzed so we can see that an increasing score in mobility suggests recovery. The device satisfies our criteria and constraints in that it's wearable and can be put on with only one arm. The fabric is non-restrictive and lightweight, so it doesn't contribute to pain in the affected arm. The data collected from the embedded sensors are accurate and reliable, and the market price of the device is around $300, which is relatively affordable for the majority of patients. So as an intended medical device, it is crucial to consider the feasibility of the device from the perspective of the patient. So the device ensures patient comfort by being lightweight and a flexible material, which will not restrict any movement, thereby encouraging recovery. The smart sleeve is adjustable so that the sensors can be moved into the correct placement on any person, regardless of their size. We also took into consideration patients living at home, in that if the patient lives alone or is otherwise unable to use this device without external help, we ensure that the smart sleeve is easy to put on and to take off independently and only with one arm. In terms of manufacturing, we used inexpensive materials to make the product financially accessible to majority of the patients. And finally, the smart sleeve is minimalistic, making it compatible with religious articles of clothing such as hijabs and burqas and clothing of the sort.
So moving on to performance testing, I will be showing the performance of the device through our demo video and going through the device operation step by step. So initially, when the device is booted up, both LEDs are on, indicating that we are in the waiting state and that the device is idle, waiting for the user to initiate a test. Once we press the button, we enter the first stage of calibration, where the user is asked to perform movement in all planes of motion, since we found this helped stabilize the sensor readings prior to the actual calibration. So once the button is pressed again and this stage is complete, we enter the second stage of calibration, where we average the sensor values to gain a reference, a 0 point for our data collection. Once data collection begins, the green LED is flashing, indicating that we are sampling values. And as you can see, as Richard is moving, the serial monitor is updating angle values and showing angles in different planes of motion, namely extension, abduction, extension or flexion, depending on which way he moves, abduction, as well as shoulder elevation. So moving on from here, the results can be displayed in the serial monitor of the Arduino. So the most recent maximum angle value of the latest session is displayed as the last value. However, these results are somewhat difficult to interpret, so we decided to use MATLAB to help better interpret these results graphically. And we made use of a Python script to export these results to MATLAB. So this is what a MATLAB result would look like. So the graph is showing maximum range of motion versus the session number in each plane of motion examined. So we have flexion, extension, and abduction. And so the session number can be in days or whatever the frequency of testing the clinician suggests. And so as you can see, for flexion, there is a gradual improvement in maximum angle, maximum range of motion, showing that the patient is gradually improving over time. The opposite is happening with extension, where their condition is actually worsening and the maximum range of motion angles are decreasing. So this may indicate to the clinician that this area is not recovering properly and there is an issue with this movement.
All right, so given all of the feasibility testing and the physical testing, we can present our overall take from the project. So we understand that it monitors movements in the coronal and sagittal planes. It keeps track of the user's highest range of motion and stores these values, and it notifies the user of improperly compensating for shoulder movements, ensuring that values obtained are accurately describing improvements in the user's ability to use those injured muscles. So overall, our device fulfilled our challenge and met the criteria and constraints that we had initially outlined at the beginning of the semester. So the feedback from mentors went a long way and suggested that the device would add value value to the rehabilitation of patients with rotator cuff injury. Feedback from the teaching team, along with our own trials, had proved the feasibility of the design. And so in terms of next steps, we'd like to take the design from a prototype to a market-ready product. That way we could properly house the components with wires, sensors, and all components inside the sleeve embedded and easy to use. We can implement monitoring capabilities in more planes, like the transverse plane, to monitor internal and external rotation of the shoulder. And we can finally have the device connect to a computer wirelessly for remote monitoring by a healthcare provider. With these in mind, we could take this to the clinical realm and be able to use this with patients who actually suffer from rotator cuff injury. Thank you very much for listening to our presentation.